Here we are. So, welcome all, and welcome to this last lecture in our series of Digital Humanities After Hours. And I'm happy to welcome Katarzyna and Kapitan from Paris, who is going to talk about teaching a computer to read medieval Icelandic manuscripts. So, Katarzyna, welcome.
Thank you very much. Thank you for the invitation, and thank you for being here, those of you who are here in person and those who are online. So my name is Katarzyna Kapitan, and this is the last of this year's Digital Humanities After Hours, so it's a great privilege to close this semester series of exciting talks at the Center for Digital Humanities at the University of Iceland. In my talk today, I will present basically an ongoing research project which is conducted within the framework of my current junior chair in computational analysis of written culture at École Nationale des Arts in Paris. And it's funded by the French National Research Agency, ANR. And as you see on this slide, the subject of this talk is quite self-explanatory. So we'll be talking about teaching computer how to read medieval Icelandic manuscripts, a do-it-yourself approach. Without further ado, my presentation is divided into three very brief parts. An introductory part with some basic background information on the project and on state-of-the-art, so to speak, followed by a presentation of some of the experiments we've conducted with Icelandic materials and the results we achieved. And then I will close with some of the perspectives, how text predictions can be used in research and where we're going with our project further. So what are the future steps? So let me start with some background. Well, I guess to this audience, I don't need to explain that even though medieval Iceland is associated with Vikings and volcanoes and glaciers, not everyone knows that it's also a home to this fantastic and really impressive cultural production of literature in vernacular, and also production of countless manuscripts which preserve texts in vernacular. While there is over 900 of Icelandic manuscripts produced between 12th and the 16th century, only a fraction of them has been edited, and even fewer have been edited digitally. But what is pretty fantastic is that pretty large part of those manuscripts, at least 50%, have been digitized. So we have those high quality images which are available online. And this opens a new research possibilities. And here I'm thinking about the possibility of working with texts as preserved directly in the manuscripts rather than in the editions of texts. Those of you who are familiar with my work will know that I'm interested in the transmission history of texts, broadly understood, so including digital scholarly editing and computational stemmatology. On this slide, you see one of my digital editions with critical apparatus and an unrooted stemma underlying my investigation of the transmission history of Hromundar Saga Gripssonar, which was published last year. So my work on this project was computer assisted, but very little has been actually automated. And because of this, it involved enormous amount of manual labor, especially in terms of transcriptions of various manuscripts. Therefore, today, as part of my current chair, together with my team, we're developing a pipeline for automated transcription of manuscripts. And this will hopefully make future projects studying transmission history of texts a bit more manageable. How? Well, by using text predictions. So what is a text prediction? It is an output from a computer model which basically learned how to read, or rather how to recognize characters. what we basically need is OCR, so optical character recognition for medieval manuscripts. Today, OCR for printed text is an inbuilt feature of many commercial programs, and we sort of take it for granted. We know it still makes errors, but we can live with those errors because the benefit outweighs the disadvantages of having those errors in the transcription, right? So on this slide, you see a digitization of 1965 edition of Erek's Saga, together with its OCR output, which, well, I think is pretty good. It's available through Bækur.is, so Landsbókasafn Íslands is behind the digitization of this edition. And, well, today I want to present to you a vision of tomorrow, so to speak, where I hope we can get similar, good enough text predictions from medieval Icelandic manuscripts. But before I go any further, I would like to ask you to look at this slide for a second and compare the text prediction on the right-hand side of the slide with the photo of the actual printed edition on the left. So what do you think about this text prediction? Is it good or bad? Just take a minute, read it, and tell me what you think. I intended to have interactive feature on the next slide, but since there is a delay between online and on-site, I think we're going to skip the interactive part, and you will only have the privilege of telling me what you think. So what do you guys think? Is it good or bad?
Quite decent, isn't it?
Decent.
Like, hands up, good? Good?
It's good, but not great.
Bad? Not bad. So, not too bad, right? Yeah. So basically, when you look at the text as a human reader, you can make the text out, right? But then if you actually focus on how many errors or something that can be considered errors in this OCR, it becomes unacceptable for many of us, right? Because in this very short excerpt, we have 295 characters with 27 errors. So this would give us an accuracy of 91%. So character error rate of around 9%. But well, the reason for this score here, of course, this is not how you would evaluate a model's output. This is just to demonstrate the dissonance between human reader being able to read the text and filling in the gaps, and evaluation of the text prediction from models, right? Something that you can read and make sense can still have around 9% character error rate. And can you guys tell me, that was another part of the interactive exercise, for what kind of tasks this text prediction could be used? Text prediction of this quality. What is it useful for? Why Bækur.is includes it?
Basically just for reading, because when you try to actually make a regular text out of it, you have to either do a lot of find and replace,
Mm-hmm.
and then it's manageable, or you have to, yeah, do it by hand.
Any other ideas? What would you do with why there is OCR? Very basic principle, why there is OCR behind those books?
Entity recognition, so if you're looking for something.
You could use it for entity recognition, but even more simple, searchability, exactly. And of course, there is research that shows that a lot of tools for text analysis can handle 9% error rate when you are looking for text reuse. For instance, you can adjust the window of your search pattern and then still use it for your computational analysis. But yes, the very basic principle is to be able to search within those editions, and it's of enormous help to researchers, right? So why I'm showing you this here? Well, this is just to put in context everything else I'm going to show you today, because while HTR, so handwritten text recognition, or ATR, automatic text recognition, has been around for 3 decades or so. Old Norse Icelandic has so far received rather limited attention from the ATR community. There has been some work done for early modern and modern Icelandic, and I believe you guys heard a talk about it just 2 weeks ago here by Johannes. So I won't be going into details of that project. But well, to the best of my knowledge, no dedicated ATR model for Old Norse Icelandic yet exists. Meanwhile, today, for other languages and other medieval manuscripts, we have some models that already match the desirable accuracy or acceptable accuracy of OCR models. So this, 95% accuracy, this is something that we can already get for medieval manuscripts. So on this slide, you have 2 versions of, well, I never know how to say this name, Bicerin. How Italians call this type of coffee around Torino? Bicerin model, which was developed by Ariane Panche and her colleagues in Lyon and in Paris. And they have the accuracy of about 95% for in-domain manuscripts. The caveat here is that your manuscript needs to be in French, and it has to be as perfect as the manuscript you see on this slide, right? So it has to be in the terms of its state of preservation, it has to be really well preserved. In terms of its layout, it has to be very clear layout, and the script type. This is, of course, beautiful Gothic manuscript that we all enjoy reading. But, well, as we all know in this room, this is not the case with Old Norse Icelandic manuscripts, right? Nevertheless, I believe that there is hope for Old Norse Icelandic as well. And I think this hope comes in the form of generic ATR models that have been developed in recent years for other medieval Latin scripts. So many of you might be familiar with Cadmus Medieval, developed by Ariane Panche and her colleagues, or with Medieval Scripts model developed by Tobias Hodel and his colleagues, both covering very wide time span of the Middle Ages, multiple medieval languages, and multiple script types. These models want to be as generic as possible. They are based on very diverse data sets, and because of that, they should be relatively easy to fine-tune for specific corpora. While we would like to think about these models as being language agnostic, as they should just work for any text in medieval script, so something that it has been trained on. If it's Gothic textualis, it should read Icelandic Gothic textualis. Well, it doesn't seem to be the case. During Transcriber Quest 2024, together with some colleagues, we had the chance to test the performance of Cadmus Medieval on Old Norse Icelandic manuscripts, and well, we weren't impressed by the results. The text prediction by out-of-the-box Cadmus Medieval was, well, mostly gibberish, and even the competence visualizations on this slide, which are inbuilt feature of scriptorium, show you that, okay, model knows that it's not very accurate, that those predictions aren't good text predictions. So when we evaluated the actual performance of Cadmus Medieval on our corpus, it scored somewhere between 65 and 68%. So I'm sure you agree that, well, this score should be easy to improve. But the question is, how easy? So this is basically the talk I'm going to give you today about what were our goals behind the experiments I'm presenting. So basically we wanted to evaluate how much data is needed for fine-tuning of generic models to achieve somewhat satisfactory results for Old Norse. So basically to get an impression how easy fine-tuning is for individual scholars with limited resources. Additionally, we wanted to create and publish third ground truths and models following the FAIR principles. We wanted to get the ball rolling for HTR for Old Norse, so more people become familiar with it and perhaps want to contribute to producing training data and exchanging best practices. And this is basically this mysterious do-it-yourself approach mentioned in my title. If we want ATR to work for Old Norse, we have to do it ourselves. There is no shortcut, and there is no point in waiting and believing that somehow generic ATR models or VLMs will become so good that they'll just read medieval Icelandic without our input. They most likely won't. And on another level, it's also do-it-yourself with reference to individual scholars who might want to fine-tune existing models for their individual projects without support from research software engineers or without access to GPUs. I'd imagine that they'd like to know how much work they need to put into this to get somehow satisfactory results. Okay, so how did we go about achieving our goals? This is what the second part of this talk is about, and it is a micro case study, okay? We designed a micro case study in which we used 2 Icelandic manuscripts, and on this slide you see some basic information about these manuscripts. Both were written in Gothic textualis. One is from the 13th century, the other one is from the 14th century. One is in a single column, the other one is in double column. We used 8 pages in total, so just 4 pages per manuscript, to fine-tune Cadmus Medieval and see whether we can gain some value by doing so. For testing, we created equally small data set, including in-domain and out-of-domain test sets. So we added 2 pages from the manuscripts we used in training to evaluate in-domain accuracy, and we added 2 more manuscripts that we used 2 pages from 2 other manuscripts to evaluate out-of-domain accuracy. And as you can see on this slide, then again we added manuscripts in textualis from 13th and 14th century in single and double column. Since we were mainly interested in the question how small can be the sample to deliver some sort of improvement, we trained the model incrementally and evaluated its performance at each step. So on step 1, we just basically tested the performance of out-of-the-box Cadmus Medieval, and we got the 65% accuracy for our in-domain set and the 68 for out-of-domain test set. Again, this is our data set, not Cadmus data set that we're evaluating on. And then on step 1, we trained on 2 pages from our corpus, so 1 page per manuscript from the training data set. Then on step 2, we trained on 4 pages, then 2 pages per manuscript. Step 3, 6 pages. Step 4, 8 pages. So this slide illustrates how the accuracy increases step by step. And you can see that the steepest climb is already after the first page. As soon as the model saw Icelandic, it was like, oh great, so now I know what to do with it. And then it continues to climb, but it's not equally steep. So the lines we're looking at here, we're interested mainly in the lines at the top because this is accuracy for characters, while the accuracy at the bottom is for words. And we know that while word division in manuscripts in general is quite a difficult task, even for human transcribers, so forgetting about the models. But you see increasing accuracy also in the word accuracy. Okay, so in my view, this is already a great success, right? especially if we focus on in-domain manuscripts, because as you can see on this slide, and this is again just a screenshot from a scriptorium interface, our fine-tuned version of Catmus produced, well, some pretty great lines. And of course, this line is cherry-picked. I was looking for a line that has just 2 errors or 1 error. So you are comparing manual, our model with Catmus medieval, and you see that we managed to get some pretty decent lines. But basically, what I want to emphasize here is that all training for these experiments were done on this very MacBook Air from 2020 that costs some 1,000 euros. So this is really do it yourself for your own project. If you think you need it, it's doable on a very small scale. Because then when you already start with an existing model, it doesn't require access to GPU. It's really tweaking of small things, and you are getting acceptable results, I think. And this makes the ATR technology more accessible. Well, but at the same time, we have to keep in mind that for out-of-domain manuscripts, we gain the improvement of only 10 percentage points. It's always something, but, well, not so amazing, right? This confirms that this approach works best in situations where we have just 1 or 2 manuscripts we want to work with, and we fine-tune specifically for those manuscripts. And however, this is definitely not the way you would like to create a generic model for Old Norse. Nevertheless, we published our data on Zenodo. We published our model on Zenodo. So anyone interested in just checking out how it performs on their manuscripts, they just take it. They can plug our model to a scriptorium and run the test prediction and decide whether this is useful for them or not. Or if they want to build further, please do. We would be delighted if you did. Okay, so this brings me to the final part of my talk. Based on these experiences and lessons learned, we are better prepared to work on a dedicated model for Old Norse Icelandic and to produce standardized data to be incorporated in the next iteration of Catmus. However, there are some things to consider which are important from a research perspective. So, originally, we decided to add multiple special characters which are important for Old Norse Icelandic manuscripts. Among them, there were obviously those representing the phonemic system of Icelandic, with vowels introduced by the first grammatical treaties, the fricatives like thorn and f, which you don't see in continental manuscripts. But also some characters which you see in continental manuscripts, but are ignored in Catmus medieval because they are not important for their research questions usually. So as an example of that, I can mention Arutunda, which for Icelandic manuscripts is actually quite useful if you are interested in dating and the distribution where Arutunda appears in the word. At the same time, to minimize the number of classes, we were not equally inclusive for all types of special characters you can find in Icelandic manuscript, but not only Icelandic manuscripts. So, for example, the distinction between straight back D and rounded D is not preserved in our training data. And this decision seems to confuse our model. As illustrated on this slide, when a manuscript contains a rounded D for the sound, our model transcribes this as F, because the new character it saw was F. So now everything probably that is with curved back would be transcribed as F. So here riddarunum becomes, I don't know, ritvarunum. So this is something to keep in mind when you define the guidelines for your ground truths, which characters you want to include and which ones are important for your research project. Therefore, currently we're building a data set which will allow us to train models on different levels and different configurations to test the performance. So ideally, we would like to assess the impact of increased number of classes or increased number of characters on the performance. So we have experiments scheduled for that in January. So we hope to have some interesting results soon. But those results will hopefully facilitate further discussions about the trades-off between data modeling and the ability to address specific paleographic questions. For example, regarding the chronological distribution of Arotunda, Insular F, or Ancial D. Are your research questions within your project dependent on knowing whether it's a insular F or not, or are you just interested in a text and you don't care what shape of an F is in the manuscript? Because at the end of the day, it all boils down to your research questions that those text predictions are supposed to help you to answer. So let me turn very briefly to the possibilities that text predictions offer to researchers today. What can we do with them beyond one day being able to search for words or phrases within hundreds? So the Union Catalogue of Landsbokasamlingen, Stockton Arna Magnussonar and den Arnemagnetiska Samling in Copenhagen. Well, my first example, and those are very quick examples, it's a project done by my colleagues in Paris who are experimenting with using text prediction for large-scale corpus-based studies of medieval literature as preserved in manuscripts and not in editions. So on this slide, you are looking at results of correlating GDP of France in the Middle Ages with appearance of love-related vocabulary and war-related vocabulary in medieval manuscripts preserving French romances. And if you're interested in the results of this paper, I encourage you to check out the paper, which is in CHR Proceedings of 2023. But let me move to the second example, which is quite different. And it draws on the work from another group of colleagues, also in Paris, who use text predictions to train deep learning models that allow for scribal hand identification. So what you're seeing on this slide is a plot of different shapes of letter A that appear in a single manuscript. And you see that, oh, you cannot really see that, but that, believe me, that A's that have similar shape cluster together, and that those clusters roughly correspond to different scribal hands in this manuscript. So this approach provides quantitative and empirical evidence for assessing existing hypotheses concerning paleography in general or paleography on specific manuscript. And finally, as some of you might suspect, my personal hope is that those text predictions will simply simplify the editorial process involved in preparations of those digital editions that take into account the entire transmission history of a work. So when you need to transcribe dozens of manuscripts to say something about the transmission of a work. And it is my modest opinion that for this purpose, the results we are achieving already at the moment are very promising, because we should be able to automate the process of normalization of our OCR or ATR output, and then be able to automatically align multiple witnesses of the same work, and this would be already a great help to editors. Instead of manually transcribing all those manuscripts, then manually aligning them, and then manually analyzing them, we are speeding something up through automatization, and I think this is really exciting. And this brings me to my final slide, where I want to summarize what we've learned from our experiments. Well, to start with, the evaluation of our results really depends on what you want from your text predictions. And what do you want to do with those text predictions afterwards? If you're a transmission history person, I think you should be excited about the results. And even if you're a paleography person, I think you shouldn't give up hope that we might be able to help in your research. What I think is crucial take-home message here is that at the current stage of our project, we're able to basically demonstrate that even 4 pages per manuscript are sufficient for fine-tuning of existing generic models and gaining 23% point improvement in the accuracy, which I think is a success story, especially for editors of individual manuscripts, because then you manually transcribe just 4 pages and the model helps you transcribe the rest. And then you fine-tune again and again, and maybe you will get 99% accuracy at some point. Moreover, our case demonstrates that fine-tuning existing models with Kraken can be done easily, locally, on an affordable machine, without GPU access and without support from research software engineers, and without subscription to any external infrastructure. So this really highlights the accessibility of HDR to research community at large. We are finally able to offer quick open access solutions to scholars interested in incorporating HDR models into their research workflows, even if they are not directly interested in the development of HDR. They just want to use it. And I think this is great. So this is all from me. Thank you so much for your attention. Please allow me to thank all the collaborators and contributors who contributed to this project so far in very different ways. So Shahan and Ariel from Lyon and Paris, my student assistants Lucy and Adonis, and the Icelandic Transcriber Quest team from last year, Kivilchim, Chris, and Giovanni, as well as 2 recent additions to the project that we are going to do those experiments in January, Paula and Clement. Thank you so much.